So I wanted to say just a little bit about energies and interactions and the relationship to forces. So what you see here is a bunch of charges, and I can put these charges into the space here, and we can look at the electric field due to those charges. So it's pretty much what you'd expect. You put a positive charge in, and the electric field points away from that positive charge. The darkness of the color of the arrow shows how strong the field is. So it's very weak over here. You can't see it very well. And the arrows get darker and darker red as you get closer because the electric field gets stronger and stronger. But the electric field tells us about forces. For instance, if I took another charge, I'm not going to drop it in here or else it'll add the electric fields together, but I'm just going to put it in here and hang on to it. It's a positive charge. It's sitting at the location of an electric field right here, electric field vector. It's sitting in an electric field that's pointing upward and to the right now, pointing away from that first positive charge. So this positive charge, if it's sitting there near there, will have a force away from the positive charge. Similarly, if I put an electric negative charge here, right here where this negative charge is, the electric field due to that first positive charge is pointing mostly down but a little bit to the right, and the force that this charge feels, because it's a negative charge, is going to be mostly upward but a little bit to the left. In other words, the opposite of that electric field direction. So this electric field tells me about forces. Now, forces and potential energies are related to each other, and I just will remind you that from Physics 9a, we learned that the force was the negative of the derivative of the potential energy with respect to location. I put this in as a gradient here because I'm hoping that you know what a gradient function is from your calculus course. It's basically the three-dimensional version of a derivative, and because it's three-dimensional, it has a direction. So the force is the negative of the gradient of the potential energy, and the physics behind this mathematical statement is just that the force vector always points toward a direction that decreases the potential energy of the two interacting objects. So what does that tell us? I'll bring the negative charge back. The force vector on this negative charge points toward the positive charge. It's attracted to the positive charge. If the force vector points toward the positive charge, then the potential energy of this negative charge will decrease as it moves toward the positive charge. As it moves in the direction of the force, its potential energy will go down. If I pull it away from the force, its potential energy will be going up. Similarly, if I have a positive charge here, it's being pushed away from the other positive charge. So if I move it closer, its potential energy will be going up. And the direction where its potential energy of interaction between these two positive charges goes down is when I'm moving this one in the direction that the force is on it. So that's the sense in which the force vector always points in a direction that decreases the potential energy of the two interacting objects. Decreasing the potential energy of two things that are attractive is bringing them together. Decreasing the potential energy of two things that repel each other is pushing them apart. So that's what the physics behind this mathematical statement here. Now, that's about potential energies. But remember that forces tell us about interactions. The force tells us about the interaction between two particles. We can get the interaction between two particles from the charge of one of the particles and the electric field of the other one. This electric field is due to one of the charges. This charge is the charge of the other one. Two interacting things, a piece from each, an electric field produced by one, we call that the source charge. The charge of the other one, we would call that the test charge. The result we get from both of those two quantities is that we can find the force. And because the force is related to the potential energy, we can do the same thing with the potential energy. We can find the potential energy of two interacting objects by knowing the charge of one of them and the voltage due to the other one. V is the electric potential, and we measure it in volts. Sometimes you just call it the voltage. What this shows here is the voltage. It shows 4.5 volts right here. Okay, 4.5 volts. Is it going to get bigger or smaller? Well, we know that a positive charge, if I put it closer to this positive charge, the electric potential energy goes up. How do we know that? Well, we just talked about it. The electric potential energy goes down in the direction of the force on this positive charge. So if I'm moving against the force, pushing it against the force, then the electric potential energy is going to be going up. So that's for a positive charge. Of course, down here we find out that positive charge times the voltage is equal to potential energy. So if the potential energy is going up as I move toward this thing, then for a positive charge, for Q positive, if U is going up when Q is positive, then V is going up when I move closer. Well, let's see if it does. It's 4.5 here. V gets larger and larger. There, it's 29. In fact, it's get that this little thing's getting really red. It's telling us something about if it gets too close, it's suddenly 220 volts right there. So this electric potential due to a positive charge is big when you're near the positive charge and smaller, 5.3, 4, 4, when you get farther away. In fact, I can plot an equipotential, a constant potential line for 5.4, and it's a circle. Suppose, let's clear that for a second. So the electric potential gets big near a positive charge. Suppose I now throw in another charge. I'm going to let go of it. This is the total field. Let's just do a quick measurement and see the electric potential. The voltage is 3, 4, 5. It gets big near a positive charge. What about near a negative charge? Well, it's negative, and it's getting more negative. In other words, it's getting smaller and smaller and smaller as I get near that negative charge. Probably won't be surprised to find out that in the middle, it's 0. It gets bigger as you go toward the positive charge. It gets smaller than 0 if you go toward the negative charge. The lowest electric potential here is near the negative charge. The highest is near the positive charge. So that's the relation between electric potential energy, and forces.